So, hello, very good afternoon to all. And today we are going to start our new chapter that is the organic compound containing oxygen only. So, in this chapter, we are going to study the alcohol, phenol, and ether. And in the next class, we are going to study aldehyde, carboxylic acid, and ketone. Right. So, we classify this organic compound containing oxygen into two parts, that is the alcohol, phenol, and ether, and the carboxylic aldehyde and ketone. Okay. So, today, basically, we are going to do one class on this, right? So let's start with the today's session. I hope my voice is audible to all of you, right? And my screen is also visible to all of you. Okay. So let's start for the today class. What we are going to discuss today, right? Okay. So basically, if I'm talking about what do you mean by this term alcohol, phenol, and ether, and how will you classify the term that containing organic compound containing oxygen? So how will you classify them? So we have a devoted two lesson for the study of this compound. In this lesson, you will be study about the compounds containing carbon, oxygen, single bond, right? Whereas the next lesson it deals with the compound containing carbon oxygen double bond. As we see here, that is either it will be aldehyde, ketone, or carboxylic acid. So among the compound with the carbon oxygen single bond are the class of alcohol, phenol, and ether. And having the following general structure, like alcohol, we have a formula for alcohol like ROH. Similar for phenol, we have a formula like benzene and having OH group, right? And ether, we have a RO, R dash. So R and R dash can also be aromatic, right? So it can be aromatic also. R represent the alkyl group, R dash also represent the alkyl group, but it can be anything, right? If you use CH3 or you use C2H5 or even you use aromatic compound as well. So it may be different. Okay, so this is all about the introduction about the what we are going to study. That is the carbon oxygen single bond we are going to study, right? And the class of this belong to alcohol, phenol, ether. They all belong to this class of, right? Now, so if I'm classify them into the primary, secondary, and tertiary, how will you classify alcohol? So, as you see in the first figure, this represents the primary alcohol. So, how will you get to know which is primary alcohol, which is secondary alcohol, and which is tertiary? So, we can get to know by as we seen here, only one alkyl group is attached to this carbon atom. So, always to for identify the whether it is a primary, secondary, and tertiary, always just consider one thing: the functional group, the carbon which is attached to the functional group, right? They have, for example, this C is connected to this OH, and how many alkyl group is connected to this C only? So if there is only one alkyl group which is connected to this carbon, which is further connected to their functional groups, so only those carbon which is connected to the functional group where we can see, not other carbons, right? So the this is the this or we can say that this is this is an alpha carbon, right? So alpha carbon, or we can say that the this R group is donated to this carbon. So there is only one R or one alkyl group is to this carbon atom, where we can say that in secondary alcohol, we have a two alkyl group attached to this carbon atom, one and two. So we can say that this is a secondary alcohol. In this case, we have a three alkyl group attached to this carbon atom. So we can say that it is a tertiary alcohol. So by this, we can classify primary, secondary, and tertiary alcohol. So I hope this is clear to you. How will you classify the primary, secondary, and tertiary alcohol? No issue in this, right? Okay, very good. So this is how we can classify primary alcohol, secondary alcohol, and tertiary alcohol. Now, some common alcohol and their name. For example, primary alcohol. So their IUPAC name is like they having this is OH group, right? So this having this is only OH, right? So this is only OH. So this will be written as 1, 2, 3. So we will write as 2-methyl propane 1 all. So it will be written as 2-methyl propane 1 all, right? So 2-methyl. Okay. So this is 2-methyl propane 1 all. We can write as, right? This is not OH. So this is only OH, right? Okay. On the similar basis, secondary alcohol. So we can write as 2 propane 2 all. So this is named as the propane 2 all. And this is the tertiary alcohol. So we can write their name as 2-methyl 2-methyl propane to all, or we say third benzyl alcohol. This is also known as the common name isobutyl alcohol, and this is isobutyl alcohol, right? Now, similarly, if I'm talking about this, so this is not term as benzyl alcohol, or we say phenyl methanol. So this is known as a benzyl alcohol. We have this group as well. Okay, so this is known as the benzyl alcohol or butane 2-ol, or we say we can write as 2,3,3 trimethyl butane 2-ol. So these are the some some common alcohol and their names, that how should we name the alcohol. For example, here we can observe that there is CH3, CH, CH2, and CH. So we can name as 1-propanol, right? Or we say N-propyl alcohol. We can also write as, right? This is the structure of cyclohexanol. So this is the structure of cyclohexanol. Now, what are the general method for the preparation of alcohol? So how will you prepare alcohol, Vita? So this is very important thing, that how will you prepare alcohol, because questions were coming directly from this topic, because in some question the reactions were given and you have to identify from which method they were prepared, right? So the first method is, that is the halocalcanes can be converted into corresponding alcohol using aqueous sodium or potassium hydroxide or water as a nucleophile. So we already studied this thing when we are talking about the organic compound containing halogen only, right? So we already know this thing. Whenever the CH3, CH2Cl, that is alkyl halide, is treated with aqueous KOH or NaOH, then the formation of ethanol will be takes place. But in place of, let us assume, if in place of CH3, CH2, and Cl, and in the place of NaOH aqueous, if you have NaOH, right, alcoholic, NaOH alcoholic, then we know that then we get the elimination reaction and we get CH double bond CH2. Right. Then we'll get the beta elimination reaction. We'll get ethene. So always remember this, NaOH aqueous must be present. So if NaOH aqueous or KOH aqueous is present, then we'll get KCl or NaCl will be removed and we'll get CH3, CH2OH. So this is the first method by which we will prepare. Now, here we can also see that this is an example of a 2-bromobutane. So by aqueous NaOH will get 2 butane 2-ol, right? So 1, 2, 3, 4. So this will get butane 2-ol. 90% will get this product, right? So we'll get butane 2-ol. So this is the first method, or we say by the hydrolysis of haloalkane in the presence of strong base like NaOH. Okay. Now this one is also very, very, very important. That is from hydration of alkene. So how will you prepare from the hydration of alkene? So basically, hydration means what? Hydration means addition of water molecule. First point is very much clear. Hydration means what? That is the addition of water molecule. Now, in case of alkenes, hydration is the addition of H plus and OH negative across the double bond to give alcohol. So in case of alkene, what is happening now? That is the hydration is the addition of what? H plus and OH negative across the double bond of the alcohol. Right. And this alkene can be hydrated by the following method. So we have a couple of methods in the hydration of alkene. So we are going to study each one in detail. Right. The first one is the acid catalyzed hydration. So this is also very, very important. That is the acid catalyzed hydration. So how will you prepare alcohol by this acid catalyzed hydration? So basically, let us assume we have a symmetrical alkene like ethene, and if you treat it with this as H2SO4, then what you'll get? You'll get like nothing but, we know that this H2SO4 act as a nothing but H, right? And this is nothing but H negative and HSO4. So this H positive and HSO4 negative. So when you break H2SO4, it will give H plus because they have a acid, so they have a strong tendency to give H plus. Now we have a CH2 double bond CH2, right? So what tendency? So in case of alkyne, hydration is the addition of H and OH across the double bond, right? Across the double bond to give alcohol. So this will act, for example, this negative part, this is the positive part. So this will act in this. So this negative part goes to this carbon atom. Assume if this negative part goes to this carbon atom, what will happening here? This will become what this will become, beta? This will become, or we say you can give it to this only, no issue from this. So this is CH3, CH2, and this HSO4. So here is one important note here. This is CH2. This is CH3. Right. This is CH2 and this is CH3. So this is happening here. So this will become CH2 and this whole part, that is HSO4, and this double bond becomes single bond CH2. Okay. Now upon hydrolysis only as 3O plus, what is happening here? That is, this will become nothing but just wait for a minute. If this will be CH3, yeah. So this is 2, 1, 3, 4, yeah. So this will become CH3. This will become CH2, and we have OH. So we'll get ethane, right? We get ethane. No, so there is, hmm, yeah, the CH3, CH2, OH. So we'll get the ethanol. So formation of ethanol will be takes place by the acid catalyzed hydration. Right. I hope this is clear to you. That is alkene. In this alkene, this H2SO4 is breaking into H plus SO4 negative. This will attack to this bond. This will become as ethyl hydrogen sulfate. So this is known as a ethyl hydrogen sulfate. Right. Now, this ethyl hydrogen sulfate become, how will you write it as H3 in the presence of H3, or this will become CH2, CH3 and OH. So this is how you can actually write. Now, the next is acid catalyzed hydration. So what is acid catalyzed hydration? So basically the reaction proceed via the alkyl hydrogen sulfate, and this method is used for the industrial preparation of ethanol. In case of unsymmetrical alkene, the addition follows the Marconic rule. For example, here we have a 2 methyl propene, right? We have a 2 methyl propene, and in presence of H2SO4 we have H plus and H2O. So we know that OH H2O having OH negative and H positive, right? So this negative part goes to those carbon atom which contain the lesser number of hydrogen on the double bonded atom, right? So this will, if this will go to this atom, so this will become CH3, CH3, C and OH and CH2 and H, right? So 2 methyl propane 2 or this formation will be takes place, right? Always remember. Now, important another thing is that is a oxo-mercuration, or we say demercuration. So this is also very important. That the alkene react with a mercury acetate, that is mercury acetate having formula HgOCOCH3, or it may be also written as a HgOH2 in aqueous tetrahydrofurate and solvent to give hydroxyl mercury compound which are reduced to alcohol by the sodium boron hydride. So let's see the how this reaction takes place. So now the alkene is treated with H2O and the HgOS2, right? That is a mercuric acetate in presence of tetrahydrofuran. So the formation of this will be takes place. Now in step 2, when this treated with the sodium boron hydride, that is NaBH4, then the reduction takes place and the alcohol will be formed, right? So this is how will you prepare by the oxymercuration, or we say demercuration method, right? So this is a method for the preparation of alcohol as well, right? Now, the next one is the hydroboration oxidation. So when the alkene is react with the BH3, a boron hydride in THF solution, and organoborane is obtained. So how organoborane is obtained? So when the burane, or we say when the this one is treated with the alkene, right? So the formation of this will be takes place. That is called organoborane. Since BH3 has the 3 hydrogen above, the addition can occur 3 times to give the trialkyl borane. So let us assume this, consider this equation. So this is CH3, CH2, this is propene, and this is react with the BH3. This will form CH3, CHH, and CH2, BH2, right? Propyl bromine. Again, this will convert into dipropyl borane, and again, they will convert into the tripropyl propane. So total, BH3 has a 3 hydrogen bonds. So above reaction can occur 3 times to give the trialkyl borane, or we say R3B. Now the trialkyl borane so obtained is oxidized using alkaline hydrogen peroxide solution to give the 3 molecules of alcohol and the boric acid. Note that the hydroxidation is the anti-Marconic addition of water all through the reaction proceed according to the Marconic rule. So one important note here, in case of how will you prepare alcohol from alkene, we study 3 methods. The first one is the acid catalyzed hydration. in case of a symmetrical alkene, right? So we can just add the H2SO4 in this and we'll get the result. And similarly, acid catalyzed hydration also used for the unsymmetrical alkene where the addition follow the Marconi's rule. Next, we study about the oxymercuration or we say demercuration reaction. So in this alkene react with the mercury to acetate and to form this and they further reduced by the sodium boron hydride, right? Sodium boron hydride is further reduced. So produce this thing, alcohol. And the last, and this method give a very good yield of alcohol. And here also the addition takes place according to the Marconic fashion. For example, if you're considering this, that is CH3, CH2, CH double bond CH2 in the presence of mercury acetate, this will produce we know that negative part and positive part, right? So the negative part goes to which carbon atom? So having this negative part, so goes to those carbon atom which contains the lesser number of hydrogen on the double bonded. Right. So this negative part is goes to this carbon atom. So this will become HgOSC. HgOSC. Now when they treated with NaBH4, the reduction will be takes place. Right. This will be CH3, CH2 twice CH, and this is reduced to this HgOSC, and this reduced to the CH3, CH2 twice CH, CH3, and OH. So here OH will be employed. Right. So the this will be known as pentane 2-or. I hope this is clear to you. And the next is the hydroboration, where the addition occur according to the anti-Marconi rule. That is the negative part goes to the those carbon atom which contain the more number of hydrogen atom. That is just opposite to that, right? So this is all about the hydroboration oxidation, right? So I hope this is clear to you. So since BS3 has a 3 hydrogen, above addition can occur 3 times to give the tri-alkyl borane R3B, and this is shown below by the protein, right? So this is how will you get. Now, the one very important reaction is by the reduction of carbonyl compound. So this one is going to be very important. That is reduction of carbonyl compound. That how will you prepare? How will you prepare alcohol by the reduction of carbonyl compounds? Right? No. We know that carbonyl compound which contain the CO group, such as the aldehyde, ketones, carboxylic acid, and ester, can be reduced to alcohol. So aldehyde give primary alcohol, while ketone gives secondary alcohol on the reduction. So if you if the reduction takes place, then the aldehyde will give primary alcohol and ketone will be give secondary alcohol. So let's see how it takes place. So this is aldehyde, RCHO. For example, let us assume if we have CH3, CHO, right? And the reduction of this takes place. So reduction will take place in the presence of reducing agent. So H2 and palladium, this behave as a very good reducing agent, and they convert this into CH3, CH2, and OH, right? So ethanol can be converted to ethanol, right? So I hope no problem in this. Okay. So this will be converted into this. Similarly, if you take ketone and if you take the reduction of ketone with NaBH4, it will convert it into the secondary alcohol. So always remember this. If we take in ketone and the reduction of ketone, convert this into a secondary alcohol. Okay. Now, carboxylic acid and ester also give primary alcohol on the reduction. So always remember, aldehyde give primary alcohol, ketone give secondary alcohol, carboxylic acid and ester. They will give carboxylic acid and ester. They will give what? So they will give primary alcohol as well, right? So we can see that. Now, one important note here. This one is very important note. That is, the reduction is carried out using hydride reagents such as the lithium aluminum hydride and sodium boron hydride. So LiLH4 is a stronger and react explosively with water, while NaBH is convenience to handle and react slowly. So lithium aluminum hydride reduce all of the above classes of compound, while the sodium boron reduce only aldehyde and ketone and does not reduce carboxylic acid and ester. Hence, it can be used to selectively reduce. Right? So always remember this. This LiLH4 and NaBH4 both are very good reducing agent. Right? Both are very good reducing agent. And LiLH4 is a stronger and react explosively with water, while the NaBH4 is convenience to handle and react slowly. Now, lithium aluminum hydride reduce all of the above class of compound, while the sodium boron hydride can reduce only aldehyde and ketone, right? It does not reduce carboxylic acid and ester. Hence, it is used to be a selectively reduced aldehyde and ketonic carbonyl group in presence of carboxylic acid and function. Now, compound, some example below illustrate the use of this reagent. Like we have a CH3CH2 and this is CH2CHO. And now when we treat this with the NaBH4 and ethanol and H3O plus, we know that they act as a good reducing agent. So they convert this. So aldehyde and ketonic carbonyl group in presence of carboxylic acid or ester function. Right. Similarly, cyclo-2-enone in presence of LiLH4 or ether, they will convert into the cyclohex-2-enol form. Okay. So this is how will you prepare. So this is the method of preparing alcohol by the reduction. Okay. So by the reduction of the aldehyde, ketone, carboxylic acid, and ester will prepare alcohol. Right? I hope this is clear to you. Good. Now, Grignard reagent react with the methanol or formaldehyde to give a primary alcohol. Right? So the Grignard reagent react with the methanol. As we can see here, the Grignard reagent react with the methanol or formaldehyde to give a primary alcohol. So how will it give? Let me explain this. Now, let us suppose we have a methanol. Methanol, we have a like C double bond O and this having H. So let us assume we have a methanol and this react with the Grignard reagent like CH3 and this is Mg and this is Br. Okay. So what takes place in the first step? That is, we know that O is more electron active than this, and they try to shift the electron of this carbon. Similarly, carbon having partial positive charge. So here, this act as a positive, and this CH3 act as a negative. So this behave as a nucleophile. So it tends to support the carbon. So what will form, beta? So basically, this will form like CH3. This is C, and this CH3 will attach to here and this will be OMG and this is BR, right? This is OMG and BR. Now, on the further step, if you do the hydrolysis of the compound, then what you'll get, then the Mg, Br, and OH will be removed. So Mg, Br, and OH. We know that this will classify as negative and plus. So this is Mg, Br, and this OH will be removed. Now, what is left behind? So we have left with CH3, CH2, and this is nothing but OH. So this is how will you get primary alcohol in case of methanol. So when the methanol is treated or we say formaldehyde is treated with the Grignard reagent, we'll get a ethanol or we say a primary alcohol. So all other aldehyde give the secondary alcohol on reaction with the Grignard reagent, right? So only formaldehyde give primary alcohol, whether all other aldehyde, right? Whether all other aldehyde give the secondary alcohol on reduction with the Grignard reagent, right? That is CS3, CS2, MgBr. Now, with ketone, Grignard reagent give the tertiary alcohol. So with ketone, this will give a tertiary alcohol. So you want to see how it will give this? Okay, so let me explain this as well. Let us assume we have a ketone like this, right? Ketone having two CH3 group. So they having two CH3 group. Now Grignard region comes into the picture, that is CH3, Mg, and this is Br. Again, this is partial negative. This is partial bond. Again, this having tendency to accept the electron, right? So this act as a nucleophile. So what formation takes place? That is CH3, C, also CH3, and here one CH3 also come. This is nothing but O, Mg, and this is Br. Again, hydrolysis of this. If you take the hydrolysis of this, what you will get? You will get Mg, Br, OH as a byproduct, and main product, what you will get? Mg, Br, and OH. So main product you will get CH3, C, CH3, CH3, and OH. Right. So what you will get, beta? That is 2,2-dimethyl propanol. Right. Or we can write as, let's like the longest chain, that is 1, 2, and 3. So 2-methyl propane 2 all. So 2-methyl propane 2-ol. Here what you get, right? So this is what you get. That is propane 2-methyl propane 2-ol, or we say it is in a tertiary alcohol. How it is a tertiary alcohol? We can see here is a three donor group is present, right? So here three donor group is present, and due to this they behave like a tertiary alcohol, or we say this is nothing but 2-methyl butane 2-ol. So this is the method by which we can prepare aldehyde and ketone using Grignard reagent, right? So we can prepare alcohol. So for preparing alcohol from the carbonyl compounds, we basically have a two method. Either by the reduction of the carbonyl compound in presence of LiLH4 and NaBH4. Out of this LiBH4, lithium aluminum hydride, LiLH4 is the strongest reducing agent, and they can reduce both as carboxylic acid ester as well improve alcohol. While NaBH4 is a weak reducing agent, and they can reduce only aldehyde and ketone to corresponding alcohol, not benzoic and not carboxylic acid and ester. So these are some differences. And the next method, how will you prepare alcohol from carbonyl compound? That is by treating with the Grignard reagent. So when you treat carbonyl compound with the Grignard reagent, then also we can prepare alcohol. For example, when you treat formaldehyde with the Grignard reagent are very reactive, right? So they are always protected from the moistures. So when the formaldehyde is treated with the Grignard reagent, then we get the primary alcohol. Similarly, when the second prime aldehyde is treated with the Grignard reagent, we'll get the secondary alcohol. And when the ketone is treated with the Grignard reagent, we get the tertiary alcohol. So you already see the example how they will convert it into this and what is the mechanism behind this, right? So this is the two method by which you convert a carbonyl compound into alcohol. Now, fermentation. So ethanol is prepared on the large scale using fermentation. It involves breaking down a large molecule into a simpler one using enzyme. So someone maybe ask in a fermentation, what is the which catalyst you uses? So you must know the name of the catalyst, that is inverse catalyst we use. So ethanol is prepared on the large scale using fermentation. So if you have to prepare the ethanol on a large scale, you use this method called fermentation. So it involves breaking down a large molecule into a simpler one using enzyme usually, or yeast is added as a source of enzyme. So how the enzyme will come, from where the enzyme will come. So yeast is added as which act as a source of enzyme. The fermentation of sugar is shown below. Here we can say that this is sugar having molecular formula C12H2010O11. When they react with water in the presence of invertase enzyme, it will convert this into glucose and fructose, right? And this will further decompose to give the 2-ethanol. So fructose and gymase, in presence of gymase enzyme, they will further, decompose, and this will give 2-ethanol plus 2CO2. So this is how will you, right? So I hope this is clear to you. Fermentation. So how ethanol is prepared on the large scale using fermentation. So it involves breaking down a large molecule into a simpler one using an enzyme called first is invertase and later gymase, right? So usually yeast is added to a source of enzyme. So the fermentation of sugar will be takes place like sugar when they are treated with H2O in presence of a catalyst invertase, they will convert it into glucose and fructose. Then this fructose is further treated in presence of gymase. So this will convert into ethanol and CO. Right. So this is the good method for the preparation of alcohol on the large scale. Right. So I hope this is clear to you. Fermentation. Now, let's see the structure and the physical properties of alcohol. So what are the important structure and the physical properties of alcohol that we are going to study, right? So the structural and the physical properties of alcohol are the structure of alcohol is similar to that of water, right? So the structure of alcohol is similar to that of water. That is the structure of water and methanol molecule are shown in the figure. So this structure of alcohol is very much similar to that of water, right? The structure of water and methanol, as you can see in the screen, that is all both have contained two lone pair of electrons. So this is a water structure H2, right? So this is the structure of water, and this is a structure of alcohol, like CH3, CH2, and OH we have. So this is the structure of this. So both containing two lone pair. That is oxygen. In oxygen we have a two lone pair. In ethanol also we have oxygen. We have a two lone pair, right? So normally hydrogen bond is responsible for the higher boiling points of alcohol. So alcohol possesses the higher boiling point as compared to uh, haloalkane or hydrocarbons. So why they possess some exceptional high boiling point? Why they are possessing more boiling point as compared to this? So it is basically due to presence of hydrogen. Hydrogen bonding. So hydrogen bonding is basically responsible for the higher boiling points of alcohol, right? Now, hydrogen bonding among this alcohol molecule is shown here. So we can see that this one is known as a hydrogen bonding. For example, this having ROH. So this O having partial negative charge and they will attract this positive charge, right? So this bond is known as a hydrogen bond. So always remember this. This is a hydrogen bond. I hope this is clear to you how this hydrogen bonding act, right? Good. Right? So this is the hydrogen bonding among the alcohol, and due to this reason only, alcohol possesses high boiling point, melting point, and they are also soluble in water. So due to formation of this hydrogen bonding only. Now, next is that is reaction of alcohol. So basically, alcohol show both acidic and basic behavior. So let's see. So alcohol both behave both as the acid and base, and they are weakly acid, right? And a strong base such as a hydroid ion and sodium hydroxide NaH, right? So alcohol behave as a both as acid and bases, and they are weakly acid, right? So they are weakly acid. A strong base such as a hydride negative ion in sodium hydride, right? In case of sodium hydride NaH, the hydride and the base are similar to this. They are actually a strong base and they can remove the proton from the alcohol molecule and an alkoxide ion is the result. For example, here we can say that this is nothing but alcohol, ROH. Now, in presence of some base, they will form alkoxide ion, right? They will form alkoxide ion, right? For example, we have a CH3, CH2OH in presence of some base B, right? So it will convert into ethoxide ion and protonated base is formed, right? That will convert it into a ethoxide ion. When water is used as a base, the acid dissociation constant Ka and Pk can be written as, for example, ROH and H2O in terms of K and Kb, we can write as K is nothing but concentration of hydronium ion into my RO negative ion upon my ROH. So pKa is inversely proportional, inversely is equal to minus log Ka. So if the value of Ka increase, then the acidic character also increase, and the pK value decrease means basic character decrease. Right. Let me show one table so that you can know the value of this. So here we have got the value of pK. So pK indicate the value of the more the value of pK, the lesser the value of Ka, and the lesser will be the acidic in nature. So we know that that is Ka, pKa is inversely proportional to Ka, right? So if someone having a large pKa value, it definitely having less Ka value. Right, and Ka value is responsible for the acidic behavior. So out of these, minimum Ka value, which of the following for versus the minimum Ka value that is methanol, CH3OH, right? So methanol having minimum pK value means it having highest Ka value, or we say this is much more acidic. So CH3COH should be much more acidic, and this will having highest pK value. It means they having a less Ka value. So less Ka value means less acidic. less acidic. Okay. So always remember that if the value of K increase, then acidic character also increase, right? So if the value of K increase, then the acidic character also increase, and this is what the value we get, right? Now, remember one important note here, that is the lower the pK value, higher is the acidity of the compound, because more the K value. Alcohol can behave as a weak base also. They have a lone pair of electron on oxygen atom, and hence they can be protonated by a strong acid to give oxonium ion as shown in the figure. For example, ROH, so alcohol, in oxygen we have a lone pair of electron. So when the some strong acid is come, they will accept this electron and will form oxonium ion, that is ROH. So OU having the positive charge, so they will form oxonium ion as well. Right. So these are the important properties of this. Now, the formation of alkoxide. So how the formation of alkoxide will be takes place? So basically what is happening now, alcohol react with sodium or potassium metal to give the respective alkoxide, right? So alcohol react with a sodium or a potassium metal to give the respective alkoxide. For example, here we have a ethanol, and this ethanol is react with sodium to form sodium ethoxide. Similarly, when the third butyl alcohol potassium metal, then when the third butyl alcohol react with the potassium metal, they will form potassium third butoxide. So alkoxide are used in the synthesis of organic compounds. So many organic compounds are synthesized by using the alkoxide. Right. Now, this one is also very, very important. That is conversion to alkyl halide. So, sometime before we already studied how the alcohol is prepared from the alkyl halide by treating with NaOH aqueous, right? Now how alcohol converted into alkyl halide. So this one is also play a very, very, very important role, because we already studied this thing in the alkyl halide chapter. That is when the alcohol is treated with PCl5, PCl3, ZnCl2, HCl, SOCl2, then we will get alkyl halide, right? So you already know this thing. So just simple of this, right? So let's see some important thing here so that we can learn this thing, right? Just give me a 1 minute. Right. So conversion to alkyl halide, we can see. how this conversion will take place. Okay. So, when we treat 2-methyl propane 2-ol with the HCl, that is in a concentrated acid HCl, right? So, what will take place basically at 298 Kelvin? This will convert it into 2-chloro 2-methyl propane on, right? 2-chloro 2-methyl propane, right? 2-methyl 2-chloro propane. And similarly, when you treat cyclohexanol in presence of HBr, they also convert this into a bromocyclohexane. Right. Similarly, as we can see that when you convert 2,2-dimethyl propane 1-ol, they will also convert this into 1-bromo 2,2-dimethyl propane. So this is how we can convert this. Out of this all method, now this associative thionyl chloride, this play a very important role, right? This method is perfect and good method, right? Because here the byproduct are SO2 and HCl, so they can easily separate it, right? Because both are in the form of gases, so they can be easily evaporated, they can be easily separated from the product. So here there is no hard work is needed for the separation of chloroethane out of the byproduct. Now, so Lucas test. So Lucas test play a very important role in alcohol because through Lucas test only we can just test which alcohol is the primary, secondary, and the tertiary. So this Lucas test is basically used to identify which type of alcohol we have. Either we have a primary alcohol, secondary alcohol, or tertiary alcohol. So Lucas test for Lucas test we have a Lucas reagent which is used to detect the presence of which type of alcohol is present, right? So it involves the reaction of alcohol with the Lucas reagent like anhydride GnCl2 and concentrated HCl. Since the reactivity of alcohol is in the following order, we know that primary alcohol having less reactive than the secondary and the secondary is less reactive than the tertiary. So the tertiary alcohol is more reactive as compared to the secondary and primary. So basically with the primary alcohol, this turbidity does not appear, right? So with the primary alcohol, turbidity does not appear. In case of secondary alcohol, the turbidity appear after 5 minutes, whereas it appears immediately with the tertiary alcohol. So the turbidity, why turbidity appears? So this turbidity is basically due to the formation of alkyl chloride from the corresponding alcohol. So whenever the alkyl halide is formed now from the corresponding alcohol, then this turbidity will be appear. So let us assume if someone give you, right, if you someone give you three beaker, that is beaker A, and this is beaker B, and this is beaker C, right? And both of them having some alcohol on them, and someone says how you can identify which alcohol is the primary, secondary, and tertiary. So by just adding some ZnCl2, that is Lucas reagent. So when you add ZnCl2 plus HCl, which is concentrated, right? So just add this thing in all these three beaker. So in this, if no effect is present, so no effect, or we say no turbidity appear, it indicates that it is a primary alcohol. So it indicates that it is a primary alcohol. If the turbidity or effect is produced in 5 minutes, so after 5 minutes, if you'll get this result, right? So if you get this effect, then it is definitely going to be secondary alcohol. And now the beaker which will give instant result, right? Instant result. So instant result, then we can say that it will be definitely tertiary alcohol. Right. So this is how we can identify primary alcohol, secondary alcohol, and tertiary alcohol by using Lucas test. Right. And someone asked why turbidity is formed. So you can say that turbidity is formed due to the formation of alkyl halide from the alcohol. Right. Now, let's see the dehydration of alcohol and what is the mechanism behind this. That is the dehydration of alcohol. So this reaction occur in the three steps. First, the protonation of oxygen of OH group, and next the loss of water to give the carbocation, and the loss of proton from the neighboring carbon atom which produce an alkene. So this shown in the figure. So first of all, the alcohol, when they are treated with the presence of some acid, H plus, then the protonation will be takes place. So the protonation of oxygen of OH group. So the protonation of oxygen will take place. This will become OH2, oxygen having the positive charge. Now oxygen try to gain electron from the nearest carbon to do just a minute. I connect the laptop with the charger. Just give me 2 minutes. Right. So, yeah. So the first step, that is the protonation of oxygen of the OH group. So we can say that here acid H plus from the acid, the protonation of the oxygen takes place. This will become OH2. Now O become positive charge. So they want to attain their neutrality. They want to attain their neutrality. They want to remove their positive charge. So those so they attract the electron from the carbon. So carbon become the positive, right? So this carbon become the positive, and this H2O will be removed. Now, this carbon atom from the neighbor carbon atom, they accept this H plus to form alkene. So this is how the protonation will be takes place. So this is the mechanism of dehydration of alcohol. So by this we can understand the mechanism of the dehydration of alcohol, right? So dehydration to form ether. So how alcohol dehydrated to form ether, right? So basically, intramolecular dehydration of alcohol give ether. So the intermolecular dehydration of alcohol give ether. This reaction, this reaction takes place at a lower temperature than that of for hydration to give alkenes, right? For example, as we can see that this is ethanol. Now, when you treat ethanol with H2SO4 at 435 Kelvin, or let's say 443 Kelvin, we'll get alkene. Now, when we treat with the 413 Kelvin, then we'll get ether. So how will you give ether? Let me explain this. Uh, right. So when ethanol, that is CH3, CH2, and OH. Now, when they are treated with the one another molecule of ethanol in presence of H2SO4, this will form ether at 413 Kelvin. CH3, CH2, O, CH2, CH3. Their name is ethoxyethane. CH3, CH2, O, CH2, CH3. So their name is ethoxyethane, right? Similarly, if you treat this alcohol like CH3, CH2, OH at 443 Kelvin, then the dehydration will be taken place. This OH and this H will be removed from this bond. So this will become CH2 double bond CH2. So always remember this, the formation of alkene. So when they are treated with the 413 Kelvin, the formation of ethoxyethane or ether will be takes place. Now when they are treated with the 443 Kelvin, then the formation of alkene takes, right? Dehydration. So dehydration to form ether. So intermolecular dehydration of alcohol give ether, right? And this reaction takes place at the lower temperature than the dehydration of to give alkene. Okay. The next important thing is that is oxidation. So how oxidation takes place? So basically, alcohol can be oxidized to carbonyl compounds, right? So alcohol can be oxidized to carbonyl compound, that is primary alcohol give aldehyde or carboxylic acid. On reduction with the secondary alcohol give ketone. Right. So just remember this thing. Primary alcohol. So this is the oxidation. By the reduction of carbonyl compounds, that is aldehyde, ketone, or carboxylic acid, we get alcohol. Similarly, by the oxidation of alcohol, we'll get the carbonyl compound like aldehyde, ketone, and carboxylic acid. So alcohol can be oxidized to carbonyl compounds. Primary alcohol give aldehyde or carboxylic acid on oxidation, while the secondary alcohol give ketone. So remember this thing. So the tertiary alcohol do not usually undergo oxidation. Why? Because they do not have any hydrogen. So without removal of hydrogen, how can you say that the oxidation reaction takes place, right? So normally KMnO4, CrO3 and Na2Cr2O7, that is sodium chromate, right, and potassium chromate are used as an oxidizing agent. For example, we have a CH3CH2OH in presence of K2Cr2O7 and H2SO4H2O will convert this thing into aldehyde, right? Propanol. And their further reduction takes place, they are converted into carboxylic acid. So the aldehyde obtained by the oxidation of primary alcohol get further oxidized to carboxylic acid as shown above. You will study more about these classes in the next session. Then when we are going to study about the aldehyde ketone and carboxylic acid, then we are going to study some reagent that we use to stop the reaction at the aldehyde level, right? Like PCB, palladium chlorochromate, PDC, palladium dichlorochromate. So these reagents were basically used which stop the reaction at the aldehyde level and further oxidation does not take place, right? So we're going to study this thing in the next class. Now, so this is all about the alcohol. So already we cover alcohol. So in alcohol, what we study, let's quickly revise all this thing. Right. So in alcohol, we already study about the classifications of alcohol. That is, alcohol are classified into the primary, secondary, and tertiary. So if the one alkyl group is present to the carbon, which is attached to the functional group, then we can say that is the primary alcohol. If the two alkyl halide attached to the carbon, which is further attached to the functional group, then we say that this is a secondary. Similarly, if the three alkyl group is attached, we can say tertiary alkyl. And the other some common name that is we use. How will you identify by the alcohol? We use the name like suffix like we use OH as a functional group, right? For all we use. Now, general method of preparation. So, how will you prepare alcohol? So, we have a first method like the hydrolysis of haloalkane. So, by the hydrolysis of haloalkane, that is whenever the CH3, CH2Cl and they are treated with NaOH or KOH aqueous, then we will prepare alcohol. So, this is one of the good method for the preparation of alcohol. Similarly, from the hydration of alkene, so in this we get the acid catalyzed hydration which follow the Marconi's rule, and another that is the hydrobolation which follows the anti-Marconi's rule. So in case of symmetrical alkene, the ethyl hydrogen sulfate will be formed, right? And the CH2, CH3, ethanol will be formed after the hydrolysis. Similarly, in acid catalyzed hydration, unsymmetrical alkene is present, and the addition is done according to the Marconi's rule. Similarly, oxymercuration, demercuration, this also react with the mercury to acetate to form the alcohol. Now, this method is very good yield of alcohol, and here also the addition takes compound place in the Marconic fashion, right? So this is all about. Now CH3, CH2, CH2, HTOS, again mercury acetate. So this is the example which show the production of alcohol. Now, the third method that that we already studied in the alcohol is that is the reduction of carbonyl compound. So, by the reduction of carbonyl compound, we have a basically two methods from the carbonyl compound. Either by the reduction with LLH4 and NaBH4 will convert this, aldehyde into the alcohol. For example, aldehyde on reduction give primary alcohol, ketone on reduction will give tertiary alcohol, right? So this will must be remembered. Here NaBH4 is a weak oxide reducing agent, where the LiLH4 is a strong reducing agent and can reduce both carboxylic acid as well as ester. Similarly, on the carboxylic acid also give the primary alcohol and ester also give the primary alcohol. So the reduction is carried out. We already told this thing. Now, this one is also important. Some example like NaBH and how LiLH4 convert this thing. Now, from aldehyde and we're using Kirgnar agent. So this play also very, very important. Just remember here, when you take only formaldehyde. So when the methanol or we say formaldehyde is treated with Kirgnar agent, we'll get primary alcohol. What will get? We'll get primary alcohol. Just a minute. Right, we'll get primary alcohol. Similarly, when we treat aldehyde with the Grignard reagent, we'll get the secondary alcohol. And when we treat ketone with the Grignard reagent, then we'll get the tertiary alcohol and so on. So this is how will you get the primary, secondary, and the tertiary alcohol by using Grignard reagent. Now, fermentation. So this method is very important because ethanol is prepared on the large scale by using the fermentation. So it involves breaking down the large molecules into the simpler one using enzyme called invertase or gymase. So usually the yeast is added as a source of enzyme. So the fermentation reaction is like when the sugar is treated with H2 in presence of invertase, it will convert glucose and fructose. Now again, fructose is treated with presence of gymase as an enzyme, it will convert it into ethanol and CO. Right. So this is another way. Structure, there is a similar structure of that of water. Normally, hydrogen bond is present, which is responsible for the high boiling point solubility. Now, acidic basic behavior, the alcohol behave both acidic as basic, right? Now, some pKa values is given. So, on the basis of pKa value, we identify which one is the stronger acid and which one is the weaker acid. So, higher the value of pKa, lower will be the Ka, and lower will be the acidity. Because acidity values depend only upon the Ka values, right? So, if the value of Ka is more, if the value of Ka is more, then definitely they will be more acidic nature. Now, we can already know this thing, right? Now, formation of alkoxide, we also studied about the alkoxide formation, ONA. Conversion of alkyl halide, this will also play an important role where we'll study PCl3, HCl, PBr3, right? ZnCl2, HCl, and in the SOCl2, which is one of the best method to convert alkyl halide into alcohol. Lucas test we studied. Basically, Lucas test is used to distinguish between the primary alcohol, secondary alcohol, and the tertiary alcohol. So, if the alcohol is primary, it will not give any reaction. So, the turbidity does not appear. If it is secondary, the turbidity appears after the 5 minutes. Now, if it is a primary, then the turbidity appears if it is a tertiary, then the turbidity appears immediately. Again, if the alcohol is primary, no turbidity appears. If secondary, turbidity appears after 5 minutes. If the tertiary, then the turbidity appears immediately. So this is how we can identify this. Now we also study about the mechanism of dehydration of alcohol. So basically, the three-step mechanism. The first step, the protonation of oxygen of OH group. That is, the protonation of oxygen of OH group takes place, loss of the water to give the carbocation, and loss of the proton from the neighboring carbon atom which produce an alkene. Dehydration of ether, so from 413 Kelvin from the ethanol with H2SO4, also we can prepare this. Right, oxidation, so alcohol can be oxidized to the carbonyl group. Primary alcohol give aldehyde or carboxylic acid on oxidation, while secondary alcohol give the ketone. Now, the tertiary alcohol do not use the undergo oxidation reduction, and they will undergo oxidation reduction in the presence of K1O4, CrO3, Na2Cr2O7, K2Cr2O7. Right. On the further oxidation, they will convert this benzoic acid. So, if you want to stop this at aldehyde level, so we're going to study this thing in the next chapter that we have to add in a reagent like PCC and PDC that can be stop the reaction at aldehyde level only, right? So this is all about the alcohol. So I hope this is clear to you all. You have any kind of doubts, you can ask. I'll give you 2 minutes, just quickly revise all this thing. And if you face any problem, any doubt, you can ask. And after this, we are going to start our new, that is phenol, right? So anyone having any kind of doubt, you can ask better till I take some water. So you can ask any doubt. Right. So now I hope you revise this alcohol. Right. Now start with the phenol. Right. So we'll try to cover the phenol. Okay. Now, phenol as the name phenol is specifically used for the following compound, that is hydroxyl benzene. So basically for the hydroxyl benzene, we use this name phenol. Okay. Now in which one hydroxyl group is attached to the benzene ring? Okay. For example, if phenol, we have it also used as a general name for the class of compound derived from the above compound. That is phenol is a disinfectant. Phenols are widely distributed, right? They are widely distributed, used in the disinfectant. Now, nomenclature of phenol. So this one is very important because sometimes the questions were coming out of you have to identify the acidic character or increase the stability or increase the electrophilic reaction. So by the common name, sometimes the questions were coming. So you must remember the common name of at least this compound only so that it will be beneficial for you, right? For example, you all know that the IUPAC name of this compound is the first one is 2-methylphenol. But this one is also important, that is the orthocarisol. So this one is known as orthocarisol. As the OH group is attached to the ortho position, so it is known as orthocarisol. Similarly, here this will known as a metacarisol, right? This one is known as metacarisol. So orthocarisol, metacarisol, and another is known as orthonitrophenol, right? So this is the orthocarisol, or we say 2-methylphenol, orthocarisol. This is known as a 3-methylphenol, or we say metacarisol, right? And this OH and NO2 are known as the 2-nitrophenol or orthonitrophenol. Again, this OH is known as a catechol, right? Remember this name? That is catechol, right? Catechol. Or we say 1,2-benzene diol, 1,2-benzene diol, or we say catechol. Similarly, they are known as the 1,3-benzone diol, what is a restroquinol and hydroquinol. So this is known as the hydroquinol. Similarly, this is known as the 2,6-dibromophenol, and this is known as the 1-naphthenol, or we say alpha-naphthenol. So this name you must remember. These are some common name which you must remember. The above is written as this one represent the IUPAC name, right? This will represent the IUPAC name, but the downward this one represent the common name. So try to learn this common name because sometimes the questions are coming like what happened when the one Napoleon is treated with these. So you must know how to draw the structure of, right? Now, what are the general method for the preparation of phenol? So arene diazonium salts or aromatic diazonium salts are obtained by the diazonation compound of primary aromatic amines, and by from the this arene diazonium salt or aromatic diazonium salt we can prepare phenol easily, right? So let us see how will you prepare arene diazonium salt. So when the benzene amine or aniline in aromatic amine is treated with Na2 and Cl H2O in presence of 273 to 278 Kelvin, then the formation of NH2Cl, that is the benzene diazonium chloride, will be takes place. Now, this arene diazonium salt on hydrolysis gives phenol. So this arene diazonium salt on hydrolysis, it will give phenol. So when the BTC, that is N2Cl, is treated with H2O, it will form phenol, right? That is the just by boiling water, that is H2O, it will give the phenol. So first is you have to prepare the aromatic diazonium salt, that is BDC, and after treating BDC with the warm water, you'll get phenol, right? Now, the next method is that is a alkyl fusion of sodium benzene sulfonate. So this one is also very important. That is an alkyl fusion of sodium benzene sulfonate. So this was the first commercial synthesis of phenol developed in Germany in 1819. It can also be used as a laboratory method for the synthesis of phenol. Sodium benzene sulfonate is fused with the sodium hydroxide to give the sodium phenoxide, which on acidification gives phenol. So how this reaction takes place totally, let's see. So this is a sodium benzene sulfonate, right? This is SO3 and a sodium benzene sulfonate. And when you treat with the NaOH in presence of 623 Kelvin, then the formation of what will take place, Na2SO3, right? The Na2SO3 will be removed, Na2SO3 sodium sulfide, and the formation of, sodium phenoxide will be takes place. Now the acidification of the sodium hydroxide will give this thing. right? So we'll get the phenol like Na, we get the OH. So we and the acidification will give phenol, right? So this is also important method by the alkyl fusion of sodium benzene sulfonate to prepare phenol. Now, this is the industrial synthesis. So, how in industries we can prepare this phenol? So, the first one is the Dow's process. This one is a very, very important process, Dow's process. So, in this process, chlorobenzene is heated with the aqueous sodium hydroxide under a high pressure. So, sodium phenoxide so produced on acidification give phenol. So, it is similar to the previous one just to prepare sodium phenoxide. Once they get prepared by just heating, by just by just acidification, we'll get the phenol. So this method was used for the many years, but now phenol is synthesized via cumene hydroperoxide, which is discussed, right? Which is discussed below. So we're going to discuss this thing. So this method was in use for many years, but now phenol is synthesized by the hypertonic cumene method. So what is cumene? So from cumene or we say hydroperoxide. So the reaction between the benzene and propene in presence of phosphoric acid give cumene. So how it will give this beta? Because when the benzene is treated with the propyl, that is CH2 double bond CH3 in presence of 523 and H3PO4 pressure, so it will convert this into CH3, CH3, CH3. That is known as a cumene. Now cumene is then oxidized to cumene hyperperoxide. So O3, so CH3, COOH will be takes place, right? And this will be CH3, CH3. So this is known as the cumene hyperoxide. So on further heating, they will convert into, in the final step, cumene hyperoxide is treated with the 10% sulfuric acid to give the phenol and acetone on hydrolytic arrangement. So this will produce into 10% of H2SO4. It will give phenol plus propanol or we say acetone. So note the propanol is obtained is a valuable byproduct of this reaction. So in this very often byproduct as a propanol. So this one play a very important role, and this is one of the valuable, valuable byproduct in this reaction. So let's see again what are the steps to prepare alcohol from cumene. So first of all, you treat benzene with the propene, prop 1E, under the high pressure and the S3PO4, high pressure and high temperature, and the S3PO4, you'll get this. That is 1 methyl ethyl benzene, 1 methyl, or we say ethyl benzene, or we say isopropyl benzene, or we say cumene. So this is known as the cumene, that is CH3, and this one, right? Let me write this here. Maybe one H is extra here. These are formed like CH3, CH3, H. So 1, 2, 3, 4, right? This is the formula. So this is only CH, not CH3. So this is CH, CH3, and CH. Right. Now, cumene is then oxidized to cumene hyperperoxide like CH, CH3, CH3O2. So what will happen? What will produce this? This will produce nothing but this will be C, this will be OH. So two O inside between this. This remains CH3 and this also remains CH3. Again, when they are treated with the acidic medium, they will convert it into phenol and CH3, COCH3. That is acetone as a byproduct. So we get acetone as a byproduct and phenol, right? So this is how will you get phenol from the cumene, right? So in the final step, cumene hyperoxide is treated and we'll get the phenol. Now, what are the physical properties? So what are the physical properties of this? So basically compounds similar to alcohol, phenol also have a hydrogen atom linked to the electronegative oxygen atom. Thus, phenol also exhibit hydrogen bonding and hence have a higher boiling point as compared to that of hydrocarbon of the similar molecular weight. So the boiling point is around 454.7 Kelvin phenol and boiling point is 383.6 Kelvin, that is methyl benzene or we can tall B. So these are the physical properties of this, right? So compounds similar to the alcohol, phenol also have a hydrogen bond, right? Now, if I'm talking about the acidic and basic nature of phenol, we get to know that is phenol are much more acidic than alcohol. So phenol are much more acidic than alcohol. Or we say the pK value of some phenol are listed below. For example, 2-methylphenol, 2-chlorophenol, 2-chlorophenol, 2-nitrophenol, 3-nitrophenol, 4-nitrophenol, 2,4,6-trinitrophenol. So their pK value is given. So we know that if higher the pK value, lower in the Ka value. So lower in the pK value, that is the picric acid, or we say 2,4,6-trinitrophenol. So this will be with a very good acidic nature, right? So since phenol are acidic in nature, they are soluble in dilute sodium hydroxide like NaOH. So this will give sodium phenoxide plus H3. Now, the greater the acidity of phenol can be attributed to the resonance stabilization of the phenoxide ion. So the resonance structure of the phenoxide ion as is shown in the figure, right? So this represents the resonance diagram of the phenoxide ion, because we know that phenoxide ion we have a negative charge of oxygen. So due to presence of the two electrons, this will take place in the resonance participation, right? This will takes place in the resonance participation. So we can say that the electron density will be increased at only ortho and para position. So the delocalization of the negative charge over the benzene ring stabilizes the peroxide ion. So no such stabilization is possible in case of alkoxide ion, right? So this stabilization is not possible in case of alkoxide ion. That's why phenol is much more acidic than alcohol. Now, similar resonance is also shown in phenol itself, but the resonance structure of phenol are less stable as compared to those of the phenoxide ion, as they involve the separation of charges, right? As they involve the separation of charges, that's why the phenoxide ion is much more stable as compared to the phenol. And both we have a resonance, delocalization of electron will be takes place. Now, electrophilic substitution reaction. So basically the compound, the hydroxyl group is a powerful activating group, and hence phenol readily undergo electrophilic substitution reaction. So in this reaction, an electrophile, that is electron loving species, attack the benzene ring and replace one of the hydrogen atom. Since the ortho and para position of the phenol are electron rich, the substitution takes place at this position only. Two such reaction are halogenation nitration reaction. Let us now study in detail, right? So if I'm talking about the halogenation, so basically phenol react with the bromine in aqueous solution to give 2,4,6 tribromophenol, and in about 100% yield, right? So this will give. Now bromination can be limited to monobromination to give mainly 4-bromophenol using a low temperature and the less polar solvent such as the carbon disulfide. So the other product form in a minor quantity is 2-bromophenol, right? So we'll get 2-bromophenol and 4-bromophenol, and this can be achieved in the low temperature and less polar solvents such as the carbon disulfide CS2, right? So this is how we look obtain. Similarly, phenol give a mixture of 2-nitro and 4-nitrophenol or nitration with the dilute nitric acid. So if the phenol, if the nitration of phenol will take place in presence of the 20% HNO3, that is the dilute HNO3 nitric acid, so we'll get the 2-nitrophenol and the 4-nitrophenol. So ortho-nitrophenol 30 to 50%, and the para-nitrophenol will be 15%. So mixture of nitrophenol is obviously separated using steam distillation. Both these products show hydrogen bonding. In case of 2-nitrophenol, the hydrogen bonding is a intramolecular, that is in the same molecule. Where in case of a 4-nitrophenol, it is the intermolecular between the different molecules. So these are we can show that. So in the 2-nitrophenol, we can see that this is the intramolecular hydrogen bonding between this, right? That is, we have a OH and we have a NO2. So we have a OH and NO2. So this is a intramolecular hydrogen bonding will be takes place. Now, in case of a 4-nitrophenol, we have a intermolecular hydrogen bonding, right? Like how? So this will be takes place by the NO2 and the other phenol of this. So this is called the intramolecular hydrogen bonding. So intermolecular hydrogen bonding takes place in case of a 4-nitrophenol, right? I hope this is understand. You understand this thing? Hmm? Yeah. And the intermolecular hydrogen bonding is obtained in case of a 4-nitrophenol. Now, Colby reaction. So it involves the sodium phenoxide, which is allowed to absorb carbon dioxide and then heated under the pressure of CO2. So sodium salicylate so obtained, and acidification gives salicylic acid. So this is phenol. When they are treated with the NaOH in presence of sodium phenoxide and CO2, they will produce sodium salicate and salicylic acid. So by the reaction of acetic anhydride, salicylic acid yield aspirin, which is the common pain reliever. So always remember, by the reaction of acetic anhydride, salicylic acid with the anhydride, acetic anhydride, they give aspirin. So how aspirin will be produced? How aspirin will be produced? So aspirin will be produced by treating salicylic acid. Remember this, by treating salicylic acid, that is OH and COOH, right? Just wait, right? So by treating acetic anhydride with the salicylic acid, when treated with the uh, acetic anhydride and salicylic acid, so they will give aspirin. It is commonly pen reliever, right? Now oxidation. So phenol, basically phenol undergo oxidation reaction to give the product, which are different from those obtained by the alcohol. So they can be oxidized using the variety of oxidizing agent as a sodium dichromate or silver oxide to give the phenol. So Fermi salt like KSO3NO is preferred for oxidation. So if we use this salt, then the phenol is converted into a benzophenol, right? Now, some famous reaction of the phenol is Reimer-Tiemann reaction. So basically, phenol react with the chloroform in presence of a sodium hydroxide or potassium hydroxide solution, followed by the acidification to give hydroxyaldehyde. Right. So phenol react with the chloroform in presence of a sodium hydroxide, or we say potassium hydroxide solution, followed by the acidification to give hydroxyl aldehyde. For example, here phenol, and when you treat with the NaOH, then the sodium phenoxide will be formed, then again with the CO2, it will form ONA and CHO. On hydrolysis, acidic hydrolysis will give salicylic. So use of a carbon tetrachloride in place of a chloroform, right? So in place of a chloroform, if we use a carbon tetrachloride, then what you will get the salicylic acid. So always remember this. If we use this CCl4, here one important note here, this is CO, not CO2. This is KCl here. So first of all, phenol is treated with the ONA, then this will treated with the CaCl3, so the ONaCHO. So use of a carbon tetrachloride in place of chloroform gives salicylic acid. Right. Now, similar to the alcohol, phenol react with the carboxylic acid to give ester, and this reaction is also reversible in nature. When the 2-hydroxybenzoic acid is treated with ethanoic acid, then the acetyl salicylic acid is formed. This reaction is an acetylene reaction, as the H or OH of the phenol is replaced by the acetyl CH3COO group. Now, the one more and last important reaction is that is the coupling reaction. So phenol react with the aromatic diazonium salt, slightly alkaline condition to give a azo compound. So these azo compound are a bright colored and are used as a azodite. So how this reaction will take place? So here this is nothing but benzenium diazonium chloride, and this is known as a phenol. So we know that how this reaction takes place is all having one H. So this HCl will be removed and this NN bond will be takes place. So this will form orange solid, or we say paraphenyl HO or we say para-hydroxy azobenzene. So out of this, you can name it anything, right? Now, so this is all about the alcohol and phenol we have. Right. So what is ether? So we already discussed about thing. Ether contain nothing but that contain ROR group, where R and R just may be alkyl or aryl group, anything. So we can already study this thing. So we can prepare ether by the Williamson synthesize. So this is one of the important method in ether preparation. So it involves the reaction of the metal oxide with the primary alkyl halide, and the metal oxide is prepared by adding sodium or potassium metal, or we say sodium hydride to the alcohol. So this is how we can prepare. So if you treat this propanol with NaAs, then sodium carboxide will prepare, and this will is further treated with CH3CH2I, then we'll get the ether, that is. So William, since it is involved the displacement of the halide ion by the alkoxide ion, right? So this is how we can prepare this. Okay. So this is how we can prepare Williamson ether through Williamson principle. So we are cover all the important topics of the alcohol, phenols, and ether. So tomorrow class we are going to do some numerical as well, PYQ questions of advanced paper. So till you can you just revise the whole concept behind this, and we are covering all the things in a very simple way. That is alcohol, phenol, ether, all important things we already covered. So just revise this thing and try to solve the question as much as you can. Right. So let's meet in the next class where we'll discuss all these important PYQ questions and all. Till you just revise this thing. Right. So okay.